Welcome to our webinar entitled Beyond the Characterization of Surface Charge, where you will learn about the application of the Zeta potential analysis in polymer research. It is my pleasure to introduce to you my co-presenter, Dr. Inge Mühlbacher. Inge is project manager in the Division of Chemistry of Functional Polymers at the Polymer Competence Center Leoben. She has more than 20 years of experience in polymer surface characterization with her focus on zeta potential and contact angle measurements.
Thomas Luxbacher is Principal Scientist for Surface Charge and Zeta Potential at Anton Paar. He has been Product Manager for Surface Zeta Potential Analyzers for more than 15 years. At the Polymer Competence Center Leoben, we are about 120 employees, and with a turnover of 9 million euro, PCCL is one of the leading non-academic research organizations in the fields of polymer engineering and science. The research at PCCL follows the complete value chain of polymer-based materials, from the design and synthesis of functional polymers to advanced processing technologies and process parameters, to adequate characterization methods and simulation of material properties, to polymer components with tailored and predictable properties for industrial applications under demanding conditions. Together with companies in the plastics industry and universities, for instance, Montaigne University Leoben, Graz University of Technology, or Vienna University of Technology, we carry out R&D projects for innovative plastic solutions in a wide range of applications, from automotive, aviation, and packaging to solar voltaic applications.
As Inge has mentioned, I am employed at the company Anton Paar in Graz in Austria, who manufactures, sells and supports scientific instruments. Anton Paar was founded in 1922 and has grown to an international company with more than 3,700 employees worldwide. Today, the company is owned by the charitable Santner Foundation. It has an export rate of 95% and it does continuous investment into research and development. All critical instrument components are manufactured in-house in 9 producing companies, including the headquarters in Graz. As a user of an Anton Paar instrument, you will get support by either one of 34 Anton Paar subsidiaries or one of 50 distribution partners. Inge and I look back at many years of a continuous collaboration. The first contact between the Polymer Competence Center and Anton Paar was established in 2004 with a joint project on the photochemical treatment of polymer films. Inge will later present results for the characterization of these surface-activated films by the Zeta potential. Back in 2004, the measurements of the Zeta potential were performed with the first-generation instrument for measuring the streaming potential, the so-called EKA electrokinetic analyzer. The Polymer Competence Center Leoben was also involved in the evaluation of Surpass, which is the second-generation instrument for surface zeta potential analysis and which was launched in 2007. The instrument Surpass was used in many projects of the Polymer Competence Center. Here I'd like to highlight the work on biocidal surfaces as a representative application. It is not surprising that the latest version of Anton Paar instruments for the zeta potential analysis is also accessible to members of the Polymer Competence Center. Surpass 3 does not replace the former instrument generation Surpass, but complements the research facility by its presence in the Soft Matter Application Lab at Graz University of Technology. But what is the zeta potential? Let us consider the surface of a solid material, which contains a certain number of surface functional groups. We expose this surface to an aqueous solution with a known composition. Water reacts with surface functional groups and creates surface charge, For instance, a negative charge of acidic groups that get deprotonated in water. The charged surface attracts ions of opposite charge that accumulate at the solid-water interface. The model of the electric double layer describes the charge distribution at this interface and predicts a certain shear plane that separates the stern layer of immobile ions next to the surface from the diffuse layer of residual charges in the interfacial region. With increasing distance from the solid surface, we find a decrease in the net charge density that transfers into a corresponding electric potential. The electric potential at the location of the shear plane is experimentally accessible and known as the Zeta potential. The Zeta potential is determined either from the measurement of the electrophoretic mobility, which is applicable to nanoparticles in dispersion and emulsions, or from the measurement of the streaming potential that is suitable for granular media, fibers, porous material, or for flat surfaces. Here we focus on the analysis of the surface Zeta potential by the measurement of the streaming potential, which arises from the flow of liquid through a capillary. Depending on the solid sample, we apply one out of two approaches for the streaming potential measurement. In the tangential mode of measurement, we pass liquid through a rectangular flow channel that is created between two samples with a flat surface, which are mounted adjacent to each other. The liquid flow is triggered by a pressure difference, which is applied between both ends of this flow channel. In the permeation mode of measurement, we make use of the pores and voids in a porous plug of a granular or a fiber sample, and we stream the liquid through this network of capillaries. With the instrument Surpass 3, we vary the pressure in a certain range and record the streaming potential simultaneously. We start at high pressure and terminate the measurement at a reasonably lower pressure, thereby collecting a sufficiently high number of data for an accurate calculation of the slope of this linear dependence of the streaming potential on the pressure difference. This slope, the so-called streaming potential coupling coefficient, is used to calculate the surface Zeta potential by this equation of Smoluchowski.
My experience with the Zeta potential started 20 years ago. In my PhD thesis, I investigated the interactions between red blood cells and neutral polymers. Red blood cells tend to form aggregates called rouleaux or money rolls, which is a neutral process in blood circulation. The reversibility of aggregate formation is function of the force acting on these aggregates. This phenomenon is very important in a living organism. The larger the aggregates and the narrower the blood vessels, the higher force the heart has to exert to shear the aggregates apart. In certain diseases, red blood cells tend to form extremely large aggregates. It was known that neutral polymers are able to change the aggregation tendency, but little was known about the mechanism involved. To learn about the aggregation mechanism, red blood cells were put into solutions of several polymers like D-block and 3-block copolymers of polyethylene and polypropylene, dextrans, lectins, and some complexes of medical infusions. In my study, I compared the electrophoretic mobility of red blood cells measured in buffer solution with its mobility in the polymer solution. In this way, I could draw conclusions on the interactions between the red blood cells and polymer molecules. On the one hand, polymers can adsorb on the surface of red blood cells, thereby building stronger networks between the cells and therefore increase their aggregation. This process leads to a decrease in the electrophoretic mobility. On the other hand, polymer molecules may deplete from the surface and reduce the interaction among red blood cells. The mobility of the cells was higher than expected for the given viscosity of the polymer solution and correlated with a reduced rouleau formation tendency. With the help of the electrophoretic mobility, I could differentiate between polymers that preferably adsorb on red blood cells from those that help to reduce rouleau formation. For which purposes do we now use the Zeta potential analyze at BCCL? As Thomas has briefly mentioned, the first topic at BCCL that involved the Zeta potential has focused on the surface modification of low-density polyethylene by UV irradiation with a mercury lamp in an atmosphere of sulfur dioxide and air. This process is called photosulfonation and results in the introduction of sulfonic acid groups onto the polymer surface, as well as several micrometers into the polymer bulk. To characterize the modified low-density polyethylene surface, contact angle as well as Zeta potential measurements were utilized. The contact angle of water measured by the Cecil drop method decreased from 98 degrees to 30 degrees, thereby indicating the formation of a highly polar surface. Zeta potential of the modified low-density polyethylene surface shifted to less negative values, with increasing UV irritation time. This result is explained by an increase in hydrophilicity of the sulfonated polyethylene surface. The isoelectric point shifted to lower pH values, which indicates an increasing amount of sulfonic acid groups present at the sample surface. In another study, we focused on self-disinfecting surfaces and on the correlation between antimicrobial activity and the Zeta potential. Microorganisms are ubiquitous in everyday life. They stick on surfaces and they multiply into cell colonies. This causes serious problems, especially in hospitals, in food industry, and in sanitary applications. The motivation for this fundamental research was to reduce the usage of disinfectants, to control the occurrence of dangerous hospital germs, and to avoid contaminated waste. Maintenance-free sterile surfaces are promising to meet the requirements of a long-term antimicrobial activity. The mechanisms of the antimicrobial activity of polymers through mer contact and the effectiveness of so-called contact biocides is not fully understood, but it is known that the positive charges play an important role. Positive charges can be found and tuned for the family of polyoxazolines. For this investigation, we used the Zeta potential to detect functional groups of additives embedded in a polymer matrix. A set of poly-2-oxazolines steroids copolymers was prepared by microwave-assisted polymerization and acid-mediated hydrolysis. Here you see the chemical structure of poly-2-oxazoline derivatives that we investigated in this study. Poly-2-nonyl oxazoline PN100 and the series of partially hydrolyzed copolymers. 5% of the respective polyoxazolines was mixed with polypropylene and pressed to 5 by 5 cm plates of a polypropylene compounds. Subsequently, these plates were tested by contact angle measurement, again with the Cecil drop method, Zeta potential analysis, and for their antimicrobial activity. The contact angle results were translated into surface energy values. Compared to the pure polypropylene, the compound plates hardly show any difference in the surface energy. The effect of the polyoxazolines on the surface energy of the polypropylene compounds is apparently less than the standard deviation of the measurements. The compounded plates retain the hydrophobicity of the pure polypropylene sample. The next experiments we carried out were Zeta potential measurements, which helped to identify different surface properties of the copolymers, not only between the pure polypropylene and the compound plates, but also among the polyoxazolane derivatives. The isoelectric point of the pure polypropylene was detected at pH 5, and that of sample PN100 was found at pH 8.7. For the partially hydrolyzed samples with a degree of hydrolysis of 50 and 75, the isoelectric point was extrapolated to pH 13.5. The isoelectric points clearly indicate the presence of cationic functional groups on the surface. The positive charges let us expect a biocidal activity, especially for the hydrolyzed polyoxazolines. In the next step, these samples were tested for their antimicrobial activity against various microorganisms in order to find a correlation with the IB derivated from the Zeta potential measurements. Here I show you the results for the antimicrobial screening of 2 gram-negative bacteria, namely E. coli and B. aeruginosa, the gram-positive S. aureus, and the fungus C. albicans. All the test samples were sterilized with ethanol prior to testing. Testing comprised the spreading of a suspension of the test organism on the plate's surface, the incubation for 24 hours at temperature for 35 degrees Celsius, the rinsing of the suspensions into a sterilized saline solution, and the determination of the remaining colony-forming unit. The logarithmic value of the reduction factor of colony-forming units on the plate surface was used as a parameter to evaluate the antimicrobial activity of the compound plates. The positive values for the reduction factor originate from a decrease of the colony-forming units, with whilst the value of +2 representing the threshold for antimicrobial activity. The antimicrobial activity against the gram-negative bacteria E. coli and B. aeruginosa, as well as against C. albicans, shows a dependence of the degree of hydrolysis and correlates with the isoelectric point. Thomas, are there applications for the Zeta potential?
Yes, indeed, there are other applications as well. An important field of application for the surface Zeta potential analysis is the characterization of polymer membranes that are used in various membrane filtration processes, such as microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and photosmosis. These filtration processes and the corresponding membranes have manifold applications in the treatment of municipal or industrial wastewater, in seawater desalination, and in other separation and purification processes. The surface Zeta potential correlates with the ability of the membrane to reject solutes in the feed water, helps to understand the process of membrane fouling and the subsequent efficiency of a cleaning cycle, and qualifies the effect of modification of the outermost membrane surface. In order to illustrate the application of the Zeta potential analysis in this field of polymer membranes, let us take a look at a typical thin film composite membrane for nanofiltration that is capable, for instance, to reject divalent ions. The pH dependence of the Zeta potential in the presence of a 15 millimolar sodium chloride solution that mimics the salinity of river water as a feed reveals a negative charge of the polyamide skin layer of this membrane. The addition of a certain concentration of humic acid to the aqueous solution alters the evolution of the Zeta potential with pH and confirms the adsorption of these acidic entities on the surface of the membrane. Adsorption of humic acid may be unexpected since both the membrane surface and this macromolecule exhibit a negative charge. But remember hydrophobic interaction. may apparently exceed the electrostatic repulsion, thereby leading to a certain deposition of humic acid molecules that render the membrane surface more acidic. In the presence of a combination of humic acid and the divalent calcium ion, we realize another effect on the Zeta potential of the nanofiltration membrane. The isoelectric point remains unaffected, but the magnitude of the Zeta potential decreases further, which we may explain by an increase in the surface of membrane that is covered by humic acid. We can imagine that the calcium ions act as a bridging link between the negatively charged membrane and the negatively charged humic acid molecules. The surface Zeta potential is also frequently used to describe the interaction of the surface of a biomedical device or of a biomaterial with its aqueous surroundings. Among such devices, we find medical tubes or prefilled syringes for the delivery of drug formulations. Categories of biomaterials with relevance for the Zeta potential analysis are, for instance, cardiovascular or dental implants, but also soft contact lenses. As an example, let us look at the surface inside a silicone hose for the transportation of antibody formulations. The Zeta potential represents a significant interfacial charge that is negative above the isoelectric point at pH 4, which is a typical property of a pristine polymer-water interface. Note that despite of the complex geometry of a flexible tubing, we find a remarkable reproducibility of the Zeta potential. The Zeta potential of a liquid dispersion of a corresponding antibody was determined by the complementary method of the electrophoretic light scattering. The isoelectric point at higher pH is typical for a monoclonal antibody, and it offers a high sensitivity for the Zeta potential to detect antibody adsorption on material surfaces such as polymers, but also glass or metal surfaces. When we pass the aqueous solution that contains the antibody through the silicone hose, and when we record the Zeta potential simultaneously, we realize a shift of the Zeta potential towards less negative values and an increase in the isoelectric point compared to the results for the pristine silicone tube. A significant fraction of the antibody is obviously adsorbing on the hydrophobic silicone surface. We estimate a surface coverage of approximately 50% from the locations of the corresponding isoelectric points. Again, we find an excellent reproducibility for the Zeta potential despite of the dynamics that is involved in this protein adsorption process. Different strategies may be applied to suppress or even to prevent protein adsorption and therefore the loss of antibody in the drug formulation. Among these strategies, the addition of an auxiliary chemical to the antibody formulation, such as polysorbate 20, which is a natural surfactant, was considered in this case study. Indeed, the capability of this polysorbate to adsorb on the silicone surface and thereby rendering the surface more hydrophilic was hindering the adsorption of the antibody. The Zeta potential result now confirms a reduction in the surface coverage of the silicone tube by the antibody to approximately 16%. Inge will now continue with the state-of-the-art research at PCCL.
In a recent project, we looked into fiber-reinforced polymers, which are composite materials made of a polymer matrix reinforced with fibers, in our case glass fibers. Reinforced polymers have numerous applications, ranging from automotive and aircraft to marine and sport industry. In the present work provides a comparative study on the interface and adhesion properties of surface-modified glass fibers embedded in an acrylate matrix. In this study, the Zeta potential was used in the characterization of two steps of fiber surface modification. The glass fibers were provided by the manufacturer with a protective organic coating, the so-called sizing. In order to be able to carry out modifications on the glass fiber, this sizing has to be removed. In this first step, the progress in the desizing of glass fiber surface could be monitored by Zeta potential measurements. As a complementary technique, the change of the physical chemical properties of the glass fibers due to the desizing was also monitored by X-ray photoelectronic spectroscopy. Since the desizing step may damage the fiber, the morphology of the fibers after each cleaning step was further studied by scanning electron microscopy. Sized fibers exhibit a rough and inhomogeneous surface that is mainly attributed to the applied organic coating. The surface becomes smoother after the extraction with acetone and the treatment with an acidic piranha solution, which confirms the partial removal of components of the sizing. This result can be confirmed by the isoelectric point of acid-treated samples at pH 3, which differs significantly from the isoelectric point of the sized fiber at pH 5. A smooth fiber surface without any traces of the sizing is also observed after the treatment with an alkaline piranha solution. This leads to an isoelectric point close to pH 2. It should be noted that the cleaned fibers do not exhibit any surface damages. Other than burnt fibers, where the surface morphology exhibits randomly scattered residues of the sizing, these residues lead to an increase in isoelectric point at pH 3.5. From these results, it can be concluded that the chemical etching process is more efficient in the removal of the sizing than the thermal treatment under the applied reaction conditions. These results could be supported by XPS measurements. After the desizing by an alkaline piranha treatment, the glass fibers were modified by a series of surface reactions. All these steps could be monitored by Zeta potential measurements. To facilitate a covalent bonding at the fiber matrix interface, the fibers were functionalized with selected organosilines. By Zeta potential measurements, these modification steps could be monitored. By the shift of the isoelectric point from pH 2 for the desized fiber to higher pH value at 9.2. For the positively charged glass fiber surface equipped with 3-aminopropyl trimethoxysilane. The next modification step deals with the attachment of a photoactive epoxide. The isoelectric point of the modified surface shifts to pH 8.3. In the final process, a photocleavage of the epoxy groups triggered by light exposure shifts the isoelectric point to pH 7.5. After the modification step, the desized and modified fibers are embedded in a photocurable acrylate resin formulation. By performing single fiber pull-out tests, maximum pull-out force, friction strength, and apparent interfacial shear strengths are determined at the function of the coupled silane. The results reveal that the attached organosilines lead to a significant increase in the adhesion strength. In another project, we focused on the functionalization of a transparent polyethylene foil. This work was done in collaboration with a group in Slovenia in the frame of the European Resina project. The surface functionalization aims at the bonding of the OLED-based DNR biosensors on the polyethylene foil. The development of a biosensor based on fluorescence excitation requires a plastic substrate with excellent optical characteristics, such as high optical transmission in the visible range and low self-fluorescence. Polyethylene films meet these optical characteristics. However, the adhesion of short sequences of oligonucleotides used as bioprobes, which are needed to develop a genosensor on such polymer films, is rather poor. In order to overcome this challenge, we performed a physico-chemical surface modification of polyethylene films. Again, all the modification steps of the polyethylene surface were followed by Zeta potential measurements. Polyethylene films were first treated with a corona discharge. Corona discharge treatment is used to improve the bondability, wettability, and printability of polymers, particularly of polyolefin films. The reason for this improvement is the introduction of oxygen or nitrogen containing groups. The corona discharge leads to carbonyl, hydroxyl, and carboxyl groups. After the corona treatment, the samples were used immediately for additional surface modification by the attachment of functional organic compounds. By simply soaking the activated polyethylene film, we attached hexandiamine and different silanes on the surface. The surface-modified substrates have been characterized for their Zeta potential and their surface topography. The isoelectric point of the corona-treated polyethylene foil could not be detected in a reasonable pH range due to the introduction of strongly acidic functional groups, but a negative surface charge was confirmed. The polyethylene surface coated with the epoxy-treated silane exhibit an isoelectric point close to pH 3, which is the same for the untreated polyethylene foil. This silane does not introduce any intrinsic surface charge, and a similar Zeta potential compared to polyethylene is expected. We checked the surface with atomic force microscopy and could see a difference in the topography. Attachment of HMDA on the polyethylene surface leads to a pH close to 4. For this result, we conclude that the reaction was not perfect. Some remaining negative groups could be detected. In case of the attachment of the amine-terminated silanes, we could distinguish the surface by the amount of positive charges. The isoelectric point of the amino-ethyl-aminopropyl silane was highest and close to pH 7. Finally, two of the modified polyethylene foils demonstrating the best adhesion of the bioprobes have been used to prepare a genosensor for the attachment of the DNA of the insect Hermetius illucens. In a very recent study, we highlight the synthesis and post-modification of silica-based microparticles with the aim to create particles with Janus-like properties, as you can see here. Functional micro and nano-sized particles have received increasing attention and expanded their range of application in numerous fields. While several studies describe particles which are either inorganic or polymeric in nature, there is promise in particles with a hybrid character. Those so-called hairy particles typically have an inorganic core on which polymer chains are covalently grafted. They have received tremendous interest due to their potential to design systems with unique properties. The particles with Janus-like properties were synthesized by first masking the grafted silica particles through a wax-water Pickering emulsion, followed by selective UV irradiation of the unmasked particles domain. The formed carboxylic acid moieties were then used for the covalent attachment of a fluorescent biomolecule. With the Zeta potential and XPS, we confirmed the changes in the chemical surface composition of the silica particles during all the modification processes. Here you can see the synthesis procedures for the fabrication of the photoresponsive hybrid particles. We carried out two surface modification strategies. In the first approach, the immobilization of a Norrish type 1 photoinitiator with functional trialkoxysilane moieties on the silica surface run over visible light-induced grafting of a monofunctional acrylate with NBA groups. Photoresponsive polymer brushes are obtained with yield-free carboxyl groups and upon subsequent UV exposure. The second strategy was carried out by immobilization of an amino-functionalized organosilicon onto the silica surface. This reaction ran thermally induced. Ring opening reaction of the amino moieties across an epoxy comprising orthonitrophensyl ester NBA groups, selectively cleavage of the NBA chromophore upon UV light irradiation yields free carboxyl acid groups. In both cases, the carboxylic groups are exploited for the subsequent immobilization of the fluorescence protein. Again, both surface modification processes could be monitored by Zeta potential measurements. The findings could be supported by XPS results.
Thank you, Inge. Now that you have seen a series of Zeta potential results for various applications involving polymers, it is time to give a short summary on the two methods for the Zeta potential analysis. The majority of data that we have shown was recorded by the measurement of the streaming potential, and the instrument Surpass 3 is the latest instrument for the surface Zeta potential analysis at Anton Paar. A typical sample holder, for instance, for polymer films is the adjustable gap cell for creating a rectangular flow channel between a pair of samples with a flat surface. The Zeta potential in colloidal dispersions of particles is determined from the measurement of the electrophoretic mobility with the instrument light sizer 500. Liquid samples are injected in the omega cuvette, which is shown as a representative sample holder. Remember the difference in the measuring principles of these two approaches. For the streaming potential measurement, we apply a pressure gradient along a capillary flow channel or along a porous sample, while for the measurement of the electrophoretic mobility, we use an electric field as the driving forces for moving charged particles in dispersion. The Zeta potential is a powerful parameter that represents the charges on the surface and at the solid-liquid interface, and its changes upon either some material surface treatment or a change in the composition of the aqueous test solution. Single measurements of the Zeta potential at fixed pH and ionic strength may already be meaningful to reflect the effect of surface modification. This example shows the changes in the Zeta potential for virgin hair after the application of different hair care formulations. The pH dependence of the Zeta potential provides the same information but in a wider range and delivers the isoelectric point as another interfacial property that is important in natural and technical processes. The dependence of the Zeta potential on the ionic strength of a complex electrolyte, other than monovalent ions, indicates any specific interaction between these ions and the solid surface, such as adsorption, complexation, or even chemical reactions. If we exchange some electrolyte by a more complex solute, such as a surfactant, a polyelectrolyte, or proteins, we may record a kind of adsorption isotherm by monitoring the Zeta potential with increasing concentration of this solute in the aqueous solution. The monitoring of liquid on solid surface adsorption processes, a feature which is especially enabled by the surface Zeta potential analysis through a dynamic streaming potential measurement, is another mode of measurement. For recording adsorption kinetics, we measure the evolution of the streaming potential with time, thereby varying the composition of the aqueous sample simultaneously. We start with the recording of a baseline for the streaming potential of the sample, rinsed with a buffer solution at a constant pressure and a constant flow rate. And we may repeat this baseline measurement several times. We then add a certain concentration of the adsorbate to the aqueous solution, and we realize a change in the streaming potential once the solute approaches the solid material surface and decides to adsorb on that surface. After achieving adsorption equilibrium, we may exchange the buffer solution again and observe another change in the streaming potential that indicates the contributions of reversible versus irreversible adsorption.
From the present joint work between PCCL and Anton Barr, we can present you a very exciting field of application for Zeta potential measurements, which is the interaction of hair care formulations with human hair. Hair needs regular care. As you can see in these pictures, there are many different ethnics and conditions of hair: women's and men's hair, curly, shiny, colored gray, artificial and natural extensions. All these types need special care because problems as split ends, hair breakage, dullness, and frizz can only be prevented by balanced care. As a conclusion of our presentation, we want to include the dynamic streaming potential measurements in the characterization of the interaction of hair care formulations with human hair. Hair may be considered as a composite of polymers, biopolymers, and its fibrous shape makes it suitable for the permeation mode of the streaming potential measurement. First, we characterize the surface and interfacial charge of the virgin hair by BH scan of the Zeta potential. Virgin hair reveals an isoelectric point in the proximity of BH3. In the next step, we use single point measurements of the Zeta potential, commonly determined in the triplicate, to access the affinity of hair care formulations such as shampoo and conditioner towards the hair fiber. Starting with Zeta potential for virgin hair at neutral pH of the aqueous buffer solutions, we apply shampoo and observe an increase indicating the effect of adsorption of an anionic surfactant. Rinsing again with the buffer solution returns the Zeta potential to the reference value of the virgin hair, but not completely. Apparently, there remains a permanent effect of shampoo treatment of the virgin hair. Application of a conditioner reverses the sign of the charge from negative to positive. Rinsing again with buffer solution removes an excess of the conditioner and leaves the hair slightly negative charged. Application of shampoo shows the same Zeta potential of the first treatment step, while the final rinse now shows that shampooing does not fully remove the cationic component of the conditioner. Due to the sensitivity of the Zeta potential, we do not assume a large surface concentration of conditioner remaining on the washed hair. The effectiveness of the conditioner may be optimized by recording the dependence of the Zeta potential of human hair on the concentration of the cationic component, such as a polyquaternium compound, or of the final conditioner formulation. In our hair washing cycle, we have used the final concentration of 400 ppm of this adsorption isotherm. The rate of adsorption at the time needed to achieve the equilibration is finally communicated by dynamic streaming potential measurement following the addition of a certain concentration of the conditioner to the aqueous buffer solution. In order to summarize all our experience, I can say PCCL is successful using the Zeta potential measurement technology in photochemical activation steps, tracing groups with biocidal activity, monitoring cleaning of fibers, following the surface modification steps, showing functionalization of transparent foils, clarifying synthesis steps in the case of particles, understanding adsorption and desorption processes. Thank you.